In this two lectures, we shall take an overview of active galactic nuclei, and what you see in the image over here is one of the initial active galactic nuclei to be identified. Now, before we get onto the subject of active galactic nuclei, it is perhaps instructive to ask oneself, what do we mean by active galaxies? And while trying to understand the question of what we actually mean by active galaxies, one can take a step backwards and ask oneself, what is a normal galaxy? In fact, as we go along, you shall realize that almost all galaxies exhibit some form of nuclear activity. But to put it very broadly, a normal galaxy is one whose properties can be understood or explained in terms of the passive evolution of the stars. As you know, in each galaxy, stars are born and stars die. And when we understand the properties of the galaxy largely by the passive evolution of its stellar population, we call it a normal galaxy. Now, as far as active galaxies are concerned, we can broadly classify it into two categories. One is what is known as the starburst galaxies, and the other is what is called the active galactic nuclei. Now, first let us get into what we understand by a starburst galaxy. Normally, if you take a galaxy like our own, for example, the Milky Way, star formation takes place at a rate of about 1 to 2 solar masses a year. But starburst galaxies are ones where the star formation rate is much higher. It could be hundreds or thousands of times larger than that of our galaxy or normal galaxy like our Milky Way. In the image, what you see is an archetypal starburst galaxy, M82, which is one of the very well-studied ones in the universe. It's relatively nearby, just 12 million light years away. It's also a strong radio source. And right in the circumnuclear region of this galaxy is where you have an intense burst of star formation. These intense bursts of star formation cannot be sustained throughout the lifetime of the galaxy. These stars are born in the dense regions. Usually stars are born in the molecular clouds in any galaxy, which are the densest, coldest regions where gravity can make the matter collapse or the clouds collapse and form stars. Now, in these dense molecular clouds, you also have a lot of dust and gas. So when the stars form, they heat the dust, and you also see these starburst galaxies as powerful sources of infrared emission. As you know, when you probe the central regions of galaxies, when there is a lot of gas and dust, it is difficult to do it at optical wavelengths because of extinction and scattering and absorption of the light. So to go deep into the nucleus, you need to go to longer wavelengths. Infrared is better, and one of the best probes is at radio frequencies. And what you see in this image, in the middle one, the red is a false color image, is the circumnuclear or the central region of this galaxy. The radio continuum emission, when it's observed at high frequencies, you can see a lot of compact sources of emission, which are either regions of ionized hydrogen which are heated by the hot stars, or you have supernova remnants, which are the remnants of massive stars which have exploded. When you can probe further deeper with using very long baseline interferometry techniques, where you connect up telescopes across continents or across the Atlantic as well, you can look at the structures of these compact sources, and many of them turn out to be supernova remnants. You can see the shell kind of structures, and you can follow its evolution with epoch and try and understand what is going on in the central region of this galaxy. This massive burst of star formation generates hot gas, relativistic plasma, which expands, coalesces, and expands along the minor axis of the galaxy, carrying with it various components of the interstellar medium, including cold gas, the metals, and populates the general intergroup medium or the intercluster medium. So this is one class of galaxies which we consider as active. These are also often found in infrared surveys because the dust gets heated up by the hot stars which form, and they could be copious emitters in the infrared region of the spectrum. But in this couple of lectures, what we're going to focus on is the second category, the active galactic nuclei. The active galactic nuclei have more to do with activity right in the nuclear region, perhaps connected with a supermassive black hole which is lurking in the center of these galaxies. So that is the story that we are trying to understand today. And before we get further, let's try and understand what are the broad characteristics of an active galactic nucleus before we look at the kinds of galaxies which have been discovered. One is high energy output from the nuclei of the galaxies. The nuclei of the galaxies could be unresolved, are usually unresolved from ground-based telescopes, and the luminosity from the nuclear region could sometimes be more than the entire luminosity of a galaxy. And the spectral energy distributions of the energy output from this nucleus extends to the highest energies at X-rays and gamma rays. In many of these active galactic nuclei, you will see collimated jets which are squirting out from the active nucleus, and while these jets are very close to the nucleus of the galaxy, they could be moving at velocities close to that of light, and as they travels further outwards, they could be slowing down. And these jets can extend from right in the nuclear regions of the galaxy on parsec scales to over several megaparsec in size. Some of the interesting challenges are to understand not only the formation of these jets, the generation of energy, but also the transport of energy over such large distances and the role they play in the overall properties of the intergalactic medium, the evolution of galaxies, and the evolution of the universe itself. In these active galactic nuclei, you often also see prominent emission lines, and emission lines whose widths could correspond to velocities which may extend up to thousands of kilometers per second. These lines are broadened because the clouds of gas which are emitting these emission lines are moving at very high velocities. And high velocities means their motions are governed by objects which are very massive. And you can use these properties to also put constraints on the mass of the central object which are governing the motions of these line emitting clouds. You also have narrow lines which, as we shall see later, originate further out from the nucleus of the galaxy. Another important characteristic of active galactic nuclei is the variability of either the nuclear source or knots in the jets very close to the nuclear regions on time scales which could vary from days to years depending upon the wavelength you're looking at. The physical processes can vary, and the variability is seen not only in total intensity but in sources which are polarized. You can also see variability in the polarized intensity. Not only that, sometimes you not only see variability in the continuum emission across the electromagnetic spectrum, but also variability of the emission lines. And we shall try and explore what we can learn by looking at the variability of the emission lines in active galactic nuclei. Not every active galactic nucleus might exhibit all of these properties, but these are some of the signatures which lead you to identify a particular galaxy as containing an active galactic nucleus. Now, as I said a little while earlier, that the energies of these active galactic nuclei have a broad spectral energy distribution extending to the highest energies at X-rays and gamma rays. The zoo of active galaxies is indeed very diverse and rich, and this has been because of the different ways in which astronomers over the years have tried to identify active galactic nuclei, either spectroscopically or from the colors of the objects, or by looking at signatures such as the structures of the radio source if it has strong radio emission. Because radio emission, as we saw earlier, could also arise from starbursts, because these supernova remnants emit non-thermal emission, but they don't have the narrow collimated jet-like structures which we referred to earlier. Here I've just listed some of the well-known classes of active galaxies: Seyfert galaxies, radio galaxies, quasars and quasi-stellar objects, which I'll mention a little while later the difference between the two, BL-like objects, and I've also listed normal galaxies over there. And you can see over there that the luminosities of the quasars can be very high, ranging up to 10 to the power of 46 to 47 ergs per second. BL-like objects could be even a little higher, and Seyfert galaxies, radio galaxies a little lower, and these are all much more luminous, as you can see, compared to normal galaxies. And you will also notice that the host galaxies are not always the same. Seyfert galaxies are normally hosted by spiral galaxies, whereas radio galaxies are hosted by elliptical galaxies. We shall also look at that a bit more detail later, but it is this rich diversity and trying to understand these properties is what is going to be the focus of these couple of lectures. Now let's first look at the first class of galaxies that we talked about a little while earlier, which is the Seyfert galaxies. Normally, as we will illustrate again a little while later, is that if you take a normal galaxy, like our own galaxy or the Andromeda Nebula, which is our near neighbor, you will find that if you take a spectrum, which is basically the optical intensity as a function of wavelength, it will be largely dominated by absorption lines. And why is this so? This is so because what you're doing is you're getting the aggregate spectra of the collection of stars. And stars have absorption spectra because of the cool outer layers which absorb light from the inner photosphere. You may also get weak emission lines from nebular regions ionized by hot gas, but generally it is dominated by the absorption lines due to the stars. It was as early as 1908 that Fart at Lick Observatory in his dissertation noticed the optical spectrum of a galaxy NGC 1068. It's a very archetypal Seyfert galaxy which we shall keep meeting through these two lectures, and he noticed that it has an emission lines. Slipher at the Lowell Observatory had a better spectrum, and he noted that emission lines are similar to planetary nebulae. Planetary nebulae occur during the stages of evolution of stars. They are ionized gas and you have emission lines from them. But he also noticed that the lines are resolved. What lines are resolved means that it has a width. It has a large width enough to measure, which means that it has large velocities. And that was interesting itself. The spiral galaxies, which normally we understand to have absorption lines, now we see emission lines in them. But the most systematic work was done by Carl Seyfert, who drew attention to a number of such galaxies, and he also noticed that they had semistellar nuclei in them. Here is an image of NGC 4051, and you can see that a semistellar nucleus over there, which would normally be unresolved, just like a star is not normally resolved in normal sort of telescopes. So when you take short exposure photographs, you can see this stellar or semistellar nucleus more clearly so that you're not swamped by the light of all the stars in the nuclear region. So now we have spiral galaxies which have emission lines and which have a semistellar nucleus. Now this was the first indication that we're looking at something very different. And when we made detailed studies of the spectra of Seyfert galaxies, we noticed that they could broadly be categorized into two types. That one is what is called the Seyfert 1, and these have later began to be called type 1 objects. They have narrow lines with widths up to a few hundred kilometers per second, widths corresponding to these velocities, which is referred to as a narrow line region. And we also see broad lines, and these broad lines could have velocities, could correspond to velocities which are tens of thousands, 10,000 kilometers per second or so, and this is referred to as a broadline region. And the other category, Seyfert 2, they only show the prominent narrow lines. Broad lines are weak or absent. So these were the initial two broad categories, but with more detail, high resolution spectra, various subcategories, 1.2, 1.5, 1.9, the intermediate types astronomers have classified. And as you go to 1.9, these are closer to 2, 1.2 would be closer to 1. But for this set of lectures, we'll largely focus on just Seyfert 1 and Seyfert 2 galaxies. And these are, as I said earlier, referred to as type 1 or type 2 AGN. Here is a montage of different kinds of Seyferts, and you can see that they're associated with spiral galaxies, but they occur in all kinds of environments. Some are relatively isolated, some are in groups, some are interacting, and some you can also see tidal tails when they're interacting closely with them. So there were suggestions that this kind of activity, even starburst kind of activity, may be triggered by interactions with close companions, so that these interactions facilitate the inflow of gas to the central region, which leads to both the AGN activity, detailed models of which we will see later, as well as starburst activity. Although I have referred to these as two different kinds of activity, we will it is worth mentioning that they can also occur in the same object. Star formation as well as AGN activity could coexist and be composite systems. But one of the interesting things what one is trying to understand now is to try and understand, when did these AGN form, what fraction did it dominate at early stages in the evolution of the universe, and similarly for starburst galaxies as well, because the star formation history and the AGN history, the understanding of that is crucial or critical to our understanding of the evolution of the universe itself. From what I've said so far, I'll just show you a few typical examples of spectra. This is a normal galaxy. These are all taken by the Sloan Digital Sky Survey, and you can see the spectra is dominated by absorption lines and the continuum emission, which you can see over there. And if you look at this galaxy, a Seyfert 1 galaxy, NGC 5548, you can see that this spectrum is distinctly different from the other one. You can also see the broad lines, the broad H alpha and the H beta lines over there, and as well as the narrower lines can be seen in the spectrum. If I were to take a Seyfert 2 galaxy, this is what we see. You can see that the broad lines are largely absent, and what you see are the narrow emission lines. So this is what I referred to earlier in terms of the classification of the sources. Now this is an example of a starburst galaxy which has been imaged. As you can see, there's an interacting pair of galaxies giving rise to star formation in the center, a burst of star formation, and this is the kind of spectrum which is characteristic of starburst galaxies. Now, in addition to these kinds of spectra, Hickman in 1980 actually pointed out to us that if you look at the spectra of a lot of nearby galaxies, you find low luminosity AGN over there. You do see emission lines, and these were referred to as the low ionization narrow emission line regions. They were also called as low luminosity active galactic nuclei. They are of lower luminosity than the Seyfert galaxies, and you can see prominent lines of sulfur 2, low ionization, oxygen 2, 6731, the oxygen 2, 3727 line at the extreme left over there. This is an example of a liner spectra. So far we have introduced you to the kinds of active galaxies which have been classified on the basis of their optical spectra with a stellar or semistellar nucleus, and these are generally radio weak. They are, if you looked at a standard radio survey, a strong source survey, these galaxies would not be picked up. But of course today, with the kind of sensitivity we have with the existing telescopes, that you will detect radio emission from all these objects. But these are referred to as radio quiet or radio weak objects, and they are classified on the basis of their optical spectra. Now, to pick out these kinds of objects, that there were various line diagnostics which were developed. One of the very earlier ones were by Baldwin, Phillips and Turlewich, and these have been referred to as the BPT diagrams. And these have been extended by Cooley and others, and today one is also looking, because today one is looking at the high redshift universe in much greater detail with the existing telescopes than it has been ever done earlier. And once we get to the high redshift universe, your lines which come into your observable window may change. So you look at all the line diagnostics at both the local and the distant universe to try and identify what kind of AGN you're looking at and what are its effects and how do they evolve, not only amongst themselves but with cosmic epoch as well. You can see in these diagrams that the H2 region basically means galaxies where you have regions of ionized hydrogen, which are the starburst galaxies, and the Seyferts and liners are clearly demarcated when you look at these line ratios which you see in this figure. So these become important diagnostics for identifying AGN both in the nearby and the more distant universe. Now, we have had a look at what I refer to as radio quiet objects. Now we will take a jump. We took a look at classes of galaxies which are very luminous at radio frequencies. Before we do that, let me just introduce you to the world of radio astronomy. Till the advent of radio astronomy, our knowledge of the universe was largely governed by what we saw in the optical region of the electromagnetic spectrum. It was in 1933 that a young engineer in Bell Labs called Karl Jansky, who was asked to examine possible sources of noise for transatlantic communication, set up an antenna, and while doing so, he identified sources of noise as distant and nearby thunderstorms, but he also found a steady hiss which would not go away. And from careful observations, he identified this noise to be from the center of our galaxy, which really heralded the beginning of radio astronomy, and he reported the results in 1933 to the radio engineers of a radio signal apparently of extraterrestrial origin. But radio astronomy really probably took off after the war, when surveys of the sky were made. The initial surveys were largely made at Cambridge and in Australia, and there were hundreds of sources which one could sort of identify and which one could sort of image in the sky. But those days the resolutions were poor, and just with a radio blob of emission in the sky, there was not very much one could do. So the important thing was to find out if these were identified with any known optical objects. Then started the whole exercise of trying to find optical counterparts of radio sources. Amongst the initial radio sources to be identified with optical galaxies were Virgo A in the Virgo cluster, M87, that is the image you saw in the first slide, Centaurus A, Cygnus A, Fornax A, Hercules A, and these were easy to identify because in those days the resolutions were very poor compared to what we have today, and with the poor resolutions the images look very large, and for more distant objects there could be many galaxies within associated with it, whereas for the nearby galaxies it was easy to find out what the optical object was. So Virgo A was one of the first sources to be identified, Centaurus A, and with the advent of interferometry, one made high resolution images of these objects. Then one realized that the radio emission was not really from the galaxy itself, but from two lobes of emission located on opposite sides of the galaxy. So what you see over here is a high resolution image made with a very large array by Rick Perley and his collaborators, and what you see over here right in the center is the optical galaxy. A radio core is associated with it, and two lobes of radio emission with bright regions of emission at the outer edges, and narrow jets of plasma which connect the nucleus to the outer bright regions of emission called hotspots. These images, these jets were not earlier visible. It was only with high resolution, high sensitivity, high dynamic range images that one was able to image these jets. But theoreticians speculated quite early on, Roger Blandford, Martin Rees, Peter Scheuer, Malcolm Longley and others, that the origin of this emission must lie in the nucleus of the active galaxy, and energy must be squirting out in the relativistic jets from the nucleus to form the outer lobes of emission. The optical galaxy looks like a mess because of dust over there, but it is basically a giant elliptical galaxy. Just to compare, the spiral galaxies which are radio quiet were associated, the Seyfert galaxies which are radio quiet were associated with spiral galaxies, whereas these radio galaxies are associated with elliptical galaxies generally. You'll find that there are exceptions, but by and large that is true. Just to show you one or two more examples, this is another galaxy. This is Hercules A, which is at a redshift of 0.155 at a luminosity distance of 745 megaparsecs away. But when you compare this image with, when you compare this image with the earlier one, what you see is a difference in structure of the outer lobes of emission. If I were to go back, what you see in Cygnus A are bright hotspots at the outer regions of emission, whereas in this source what you see are diffuse plumes of emission with no bright hotspots at the outer edges. So these are two characteristically different kinds of radio structures, and you can see that the jets over here are more symmetric, and associated with it right in the center is a giant elliptical galaxy. Another example of this, I'll show you one or two more examples. M84, 3C272.1, 3C denotes the third Cambridge catalogue, and you can see over here that again outer diffuse plumes of emission and symmetric jets, and which are squirting out from the nucleus of the active galaxy. Lobes are fainter and lack bright hotspots at the outer edges. This is a more detailed blow up of a the galaxy which I showed you earlier in the first slide, M87, just to show you that structures can exist in all kinds of scales. What you saw in the first picture was just the central region of the image of the image on the upper left hand side, and when you look at it at lower resolution, you see more diffuse emission. When you look at it at higher resolution, you look at it finer scale structures. So when you look at it higher and higher resolution, you probe deeper and deeper into the nuclear regions, the more compact regions of emission, whereas when you look at it lower resolution, you pick up the more diffuse large scale emission. And both are interesting because both are required to find a complete and comprehensive picture of what a galaxy might look like. Here, as you keep zooming in, you will see that the jet which is in the nuclear region, and the bottommost picture is one of the highest resolution images of the jet in M87. Now the two classes here also, you do not see bright hot spots at the outer edges, but you do see a one-sided jet. So in astronomy, you'll find that there are always interesting exceptions which are a challenge to understand and explore for us. But based on the structures of these sources, Julia Riley and Bernie Fanaroff, who was at Cambridge at that time and now is leading the SK effort in South Africa, classified these objects into two broad categories which are known as Fanaroff-Riley classes. The Fanaroff-Riley class 1 object are the lower luminosity sources, absence of prominent hotspots, and they're more symmetric jets. Whereas the FR class of sources are high luminosity sources, they have prominent hotspots at the outer edges and asymmetric jets. Just to sort of give you a little bit of a physical insight, that these Fanaroff-Riley class 2 jets are believed to be moving with high Mach numbers, are highly relativistic, and they entrain less material from the surroundings, are better collimated. Whereas in the Fanaroff-Riley class 1 objects, they have low Mach numbers, low velocities, susceptible to instabilities, and also entrain more material from the surroundings. They are not as well collimated. They diffuse out rapidly to form these large plumes of emission, whereas the FR2 jets, you'll find, remain collimated and deposit their energy at the hot spots in the edges, generally in the edges of the outer lobes. More recently, there have also been a class called FR class 0, which are just compact radio sources without these huge extended lobes of emission or extended lobes of emission, and very high resolution observations show that they're a mixed bag of objects. Some have collimated structures, some are compact, and there are also sources which show both an FR class 1 and class 2 structure on opposite sides, which are referred to as hybrid morphology sources. So these are all interesting sort of aspects of these objects to try and understand their basic physics. Now, just to highlight the distinction between FR class 1 and FR class 2 objects, here are two more images. You can see first is of a radio galaxy 3CR 296, and you can see the symmetric jets, plumes of emission. At the bottom right, what you see is a quasar, which we haven't introduced as yet, but it has an FR class 2 radio structure with a bright core, a one-sided radio jet, and bright hotspots at the outer edges. You can see how well collimated the jet remains over distances of over 100 kiloparsec or so. Just to summarize, we looked at the radio properties of these objects, but one might also add over here that just as in the case of Seyferts, you have narrow line Seyferts and broad line Seyferts, you also have radio galaxies where broad lines are visible, and also radio galaxies where only the narrow lines are visible. And as we go along in these two lectures, we'll try to make some sense of that and see how that might arise in a canonical model of an active galactic nucleus. For this right now, just sort of remember that the broad line radio galaxies have broad lines as well as narrow lines, and the narrow line radio galaxies are dominated by narrow lines of emission, which are typically less than about hundreds of kilometers per second. Broad lines can extend to thousands of kilometers per second. Now, we mentioned the word quasar a little while earlier. This also was discovered by trying to find optical counterparts of radio sources. You can see that the radio window was the first major window of the electromagnetic spectrum to be opened up outside the optical region, which we were all familiar with over millennia literally. And And this one was trying to find optical counterparts of some of the 3CR radio sources. The 3C radio sources are from the third Cambridge survey, which was done at 178 megahertz at Cambridge Telescope in England. And while trying to find optical counterparts, they found that there are certain sources which look completely star-like, and they are not, galaxies have a fuzz around them, and you can make out the structures of galaxies on plates of Palomar sky survey, but these were completely star-like. But when you took a spectrum of it, then unlike stars, which as we mentioned earlier are dominated by absorption lines, in the case of these star-like objects, they were dominated by very strong emission lines. They were not only strong, but they were very wide as well. So the identification, just to recap a little bit of history, is that you need very accurate positions because these objects would generally a bit more distant. And one of the ways in which the accurate position was determined was when this radio source was occulted by the moon. And once the position was accurately determined, that one could be certain of the identification, and then the redshift was measured. But the measurement of the redshift was not very straightforward, because when the lines were first observed, it was not clear what those lines belonged to. It was Martin Schmidt who recognized that these were the redshifted Balmer lines. And then you put a redshift, you put a distance, and you find that these are amongst the most luminous objects known. These are also copious emitters in the X-ray region of the spectrum. So if X-ray astronomy had started off earlier than radio astronomy, these objects would have probably been discovered in the X-ray region of the spectrum. But in terms of stars, it looked like any other star in the sky. There would have been millions of stars brighter than 3C273, but later we learned to identify colors of quasars and also look for quasars based on their colors. So these are amongst the most luminous objects in the sky, also found by trying to look at optical counterparts of radio sources. On the right, what you see is an optical spectrum of 3C273 showing the redshifted lines H alpha, H beta, H gamma, H delta, etc. So you can see that it is neatly shifted by a redshift of 0.158 or so. So that lambda observed is equal to lambda emitted into 1 plus z, where z is the redshift. On the left, what you see is the typical quasar spectrum dominated by broad emission lines. And here again, the emission lines, as we mentioned earlier, have widths which are very broad. They are widths which could be thousands of kilometers per second. In these two lectures, we will not deal too much with the absorption lines. The absorption lines are also critical. Some are associated with the quasars, and you have outflowing winds which cause very broad absorption lines in the vicinity of the quasar itself, outflowing winds, and the quasar absorption lines are also valuable probes of the intergalactic medium. Now, as I mentioned a little while earlier, that when they first identified quasars, it looked completely star-like on the Palomar Observatory sky survey prints. But the question arose even then as to what are these objects? They are extragalactic, but they don't seem to have a fuzz around them. They're not associated, don't seem to be associated with galaxies. What are these unique classes of objects? Even from ground-based observations, people tried to see if there was a hidden nebulosity around it which might correspond to a galaxy. Although wee bits of progress were made in the early years from ground-based observations, the clinching evidence came from observations with the Hubble Space Telescope. And you'll find over here that quasar host that you get almost every galaxy where you expect to detect a host galaxy, you see hosts which are either elliptical, spiral, or they could be interacting systems, just as in galaxies in our own neighborhood. So what are quasars then? Quasars are just abnormally luminous nuclei of galaxies. Initially, the nucleus was so bright that dynamic range limited our ability to detect the nebulosity around it from ground-based observations. So even in the early days of a Hubble Space Telescope, it was a bit of a challenge because you really needed to take care of the point spread function of a very strong source in the center to clearly bring out the fuzz around it. So today we know that quasars are nothing but galaxies with abnormally luminous nuclei. And quasars came from the acronym of quasi-stellar radio source. Then you can ask yourself, what are quasi-stellar objects? Now, when we learned to identify the colors and the properties of quasars, we also made surveys of the sky to look at all quasars independent of their radio emission, and we found that that only a small fraction of these objects are actually strong radio sources. So objects which are radio weak and radio quiet, like the Seyferts, are called the quasi-stellar objects, and the luminous ones are called the quasars or quasi-stellar radio sources. This is one more slide just showing the host galaxies of the radio loud and the radio quiet. Here, as I mentioned earlier, that the quasars have both spiral, elliptical hosts. The radio loud ones tend to be in elliptical, but you can see the radio quiet ones can be elliptical, spirals, interacting systems, the whole lot. Let me introduce you now to another class of active galaxies, one of the more extreme types called the BL-Lacertae type objects or BL-LAC objects. This also came about by trying to find optical counterparts of radio sources. There is an object identified from the catalog by the Vermilion Radio Observatory in Canada, which was identified with a star-like object, just as in a quasar. But in this case, the surprise was that when they went to take a spectrum of the object, they could not find any emission lines. If it was a star, you should have seen absorption lines, a normal star. If it was a quasar, you should have seen prominent emission lines. But here was an object there was no prominent emission or absorption line at all, but the star was known to be variable in the constellation Lacertae, and that is how it got its name. Variable stars are named with 2 letters of the alphabet following certain norms and the name of the constellation. So BL Lacertae was a known variable star, but what was found was powerful radio emission from it. It was slowly established that some of them do show weak emission lines, absorption lines, and also their distributions in the sky suggested they were extragalactic objects. They are amongst the most violently variable objects. They tend to be strong radio emissions. They are also prominent in the X-ray regions of the spectrum. And these, along with a subset of radio loud quasars, which are optically violently variable, are together known as blazars. And as I said, they are strongly variable. They could vary on time scales of days or less, and they could be vary in both total intensity and linear polarization as well. The images actually show radio images of the inner sort of nucleus structure of one of the BL-LAC objects, 0735 plus 178. And these jets right in the nuclear region exhibit all kinds of interesting phenomena, which we will meet later. Now, active galactic nuclei, as we saw, are associated with both ellipticals, early types as well as late types. The early types ones are usually, the radio loud ones are usually associated with the early type galaxies, whereas the radio weak types are associated with the late type or the spiral galaxies. I must add over here that spiral, although from the nearby universe we classify galaxies as radio loud or radio weak, as ellipticals or spirals, that when you look at the more distant universe, you find that galaxies are far more complex in shape. They are interacting with one another and have a variety of interesting shapes. Powerful radio sources with jets squirting out from the nucleus also affect the properties of the interstellar medium, and what you see on the left side over here of high redshift galaxies, luminous radio sources which actually affect the properties, trigger star formation in galaxies and give rise to shapes which are aligned with the overall axis of the galaxy. So this whole feedback of radio sources affecting galaxies and the environment continues to be an interesting source of study today, and has a lot of interesting clues as to how galaxies evolve with time. Having introduced you to the kinds of galaxies and the emission from them, let us spend a little while looking at what the emission processes might be. We'll look at the continuum emission processes, which are not thermal emission, but non-thermal emission processes play a major role. And with the detection of synchrotron emission, Shklovsky and others realized quite early on that the radio emission is due to synchrotron emission, which is ultra-relativistic particles moving at nearly the velocity of light in a magnetic field are accelerated by the Lorentz force. And when you do these, when you do the sums over here, you will find that you will have to transform the emission cone from the from the non-relativistic case to the relativistic one, which leads to the emission being confined to a cone angle. The forward cone gets compressed to a half angle of theta, which is equal to 1 upon gamma, where gamma is the Lorentz factor of the relativistic electron. So you can see that when the particle or the electron is moving at relativistic speeds, the cone angle is really small, and if it was just one electron hovering around or moving around the magnetic field, you'll find that at a distant observer would see a series of pulses when the cone sweeps his or her line of sight at the Doppler shifted gyration frequency, yielding a spectrum in all frequencies of the Doppler shifted gyration frequency. And these harmonics are very closely spaced, leading to a continuum, and we will not spend too much of time looking at the detailed mathematics, but most of the energy is emitted at a frequency close to about 4.2 gamma squares and the perpendicular component of the magnetic field in Gauss. And gamma is the Lorentz factor of the relativistic electron. So here we've just put one number where gamma is the order of 10 to the power of 4, which you can see has a velocity of 0.9999999 c, moves in a magnetic field of 10 microgauss, would radiate at a frequency of 1 gigahertz, which is the standard radio frequency observed by many telescopes, including the Giant Meter Wave Radio Telescope. So this is the spectrum from a single electron. But what we see is emission across a band of wavelength. So you have energies, electrons spread over a large range of energies, and there are interesting questions to answer as to how the electrons are accelerated over a large range of with a large energy spectrum. And what we can sort of show is that if you had a power law distribution of electron energies, this would lead to a power law spectrum of the observed flux density, as you can see in this slide over here. Now electrons, when they radiate, are going to lose energy, and so the spectrum of this emission, depending upon whether energy is supplied or not, will evolve with time. But let's say that you had an initial energy spectrum which had a power law. At radiative losses, as I've written over here, the rate of loss of energy is proportional to the magnetic field, the perpendicular component of it, square of it, and the square of the energy of the electron. So the higher energy electrons would radiate energy faster, and they would also radiate at higher energies, and absorption effects would be important at low frequencies. And the synchrotron radiation, another characteristic of it is it's polarized, and the polarization could extend up to about 70%. But however, this radiation can go to lower values if it is depolarized, and depolarization can occur if, for example, the field lines are completely tangled up. You'll still see the synchrotron emission, but the degree of polarization will drop. Polarization will also drop if the field lines are going through a magnetoionic medium, where due to the effects of Faraday rotation, the field lines will be rotated by different amounts along slightly different paths of light, lines of sight or path lengths. And when you average this with a beam of a telescope, you will see a drop in the degree of polarization. So these are the characteristics of continuum or synchrotron emission. Another very important process of at these energies, particularly at high energies, is inverse Compton scattering. Inverse Compton scattering is where high energy electrons scatter off low energy photons, with the electrons losing energy while the photons gain energy. Suppose you had a photon of frequency nu, and after scattering with a relativistic electron of energy E equal to gamma me c squared, we'll have a frequency which is gamma squared nu. Okay, it's valid in a certain regime, as mentioned in a slide over there. So if you had a photon of 1 gigahertz, which you mentioned earlier, and this is scattering off a relativistic electron with a Lorentz factor gamma of the order of 10 to the power of 4, you'd have emission at about 10 to the power of 17 hertz, which is in the high energy region of the spectrum. So you can see that inverse Compton scattering is also likely to play an important role. The scattered radiation by inverse Compton scattering has a power law with a similar spectral index as that of the synchrotron source. So when both are operating, both processes could be operating. So the relativistic electrons can lose energy both via synchrotron process as well as the inverse Compton process. And the ratio is given by the ratio of the photon density to the magnetic energy density. Okay? And if the photon energy density dominates, then you'll have inverse Compton scattering dominating. If you had a magnetic energy density which dominates, then you have the synchrotron process which will dominate. And the inverse Compton scattering can take place with the radio photons themselves or also with photons of the cosmic microwave background radiation. Now this is a glimpse of, a very crude glimpse of the spectral energy distribution which we mentioned earlier. And what you see over here is at the low energy, which is at the extreme right, is a radio region of the spectrum, which is due to the synchrotron process. And you see two lines over there. The red is the radio loud and the blue is the radio weak or radio quiet ones. Infrared emission is reprocessed emission by dust, which could be dust reprocessed by stars as well as dust reprocessed by the AGN, the AGN emission being reprocessed. Ultraviolet emission, thermal emission from an accretion disk which is around a supermassive black hole. X-rays and gamma rays, both synchrotron and inverse Compton processes could play a role. In gamma rays, also hadronic processes, very high energy protons could actually play a role in the gamma ray emission. I'll briefly just mention about variability, which he mentioned as one of the characteristic signatures of AGN. And blazars are amongst the most strongly variable, and they're variable across the electromagnetic spectrum. They shine out at the highest energies and they're extremely variable. In fact, they're more variable almost across the electromagnetic spectrum. Now I've just put one example over here, that if you had variability at high energies and you could put a you could estimate a time scale of variability, that can also be used to put a length scale over which it is varying. For example, this is the time scale of X-ray variability published long time ago by Lee et al. And if you take a typical time scale of 10 to the power of 4 seconds, you'll find that the variability occurs over a time scale of 3 into 10 to the power of 12 meters, which is about 10 to the power of minus 4 parsecs. So these scale of structures are not normally accessible or be able to resolve by telescopes. And this is an interesting way of trying to probe the structures in the nuclear regions of active galaxies. The other important process of how the emission might vary very strongly is that the jets, when they're inclined at small angles to the line of sight towards us, the radio emission can get Doppler boosted due to the relativistic transformations that have to be put in place in terms of the solid angle, the frequency, the time. And what you have is an expression which is shown over here, that S observed is equal to S intrinsic, and here gamma is not the Lorentz factor of the individual electron, but a Lorentz factor corresponding to the bulk motion of knots or bits of the jet which you're observing, and beta is the velocity corresponding to it. N plus alpha, alpha is the spectral index of the non-thermal emission of the jet, and n could be either 2 or 3 depending upon whether it's a jet or an individual plasmon. And as you can see from this expression, if beta is very large and phi is small, that you could have large enhancements to the observed intensity, and small variations in beta or phi can lead to very large observed changes in intensity as well. So these jets, as well as processes taking place in the accretion disk, can lead to variability from X-rays to the radio region of the spectrum. The timescales of radio variability are usually much longer than what you see at the highest energies. Now we will look at, for the last part of today's talk, we'll look at radio galaxies and quasars in a little bit more detail. Okay, they range in size from less than tenths of parsec, buried right within the nuclear regions of active galaxies, to over several megaparsec in size. And it's important to understand the evolution of these sources, both with time and also with cosmic epoch. The interaction with the external environment, whether it be the interstellar medium of the host galaxy, or the intergroup or the intercluster medium if it is in a cluster, or whether it is the general intergalactic medium or the filaments in a cosmic web, they all play an important role in trying to understand the different constituents of the universe and its physical properties. For example, today in understanding clusters of galaxies and how they evolve, that the energy input from AGN it plays an extremely important role in terms of the evolution of the intercluster medium in clusters of galaxies. So feedback by interaction within the host galaxy also, as the jet expands outwards, is important. Now today, for example, I mentioned earlier that when in high luminosity sources, when the jets traverse outwards, you can see structures aligned with this radio jet because it triggers star formation along its way. But there are also models which say that these jets heat up the interstellar medium to high enough temperatures, preventing it from collapse and preventing star formation to take place. So it is important to try and understand the physical conditions in which in one case one might trigger star formation, and in other cases where one might actually inhibit star formation. So these are aspects which are really sort of areas still to be explored to a high to have a high degree of consensus on what might be happening. Now typical radio spectra, these are spectra of actually small sized radio sources, and what I have indicated over here are you can see spectra which are straight, spectra which turn over at lower frequencies because the emission gets absorbed either by plasma due to free absorption, by thermal plasma, or a process called synchrotron self-absorption as well, where the synchrotron photons get reabsorbed. And also at high frequencies, what is not very clear in this picture, but we'll see later, is that due to radiative losses, the spectrum will steepen unless there is a fresh supply of high energy particles over there. The sources start out small, buried within the nuclear regions of the active galaxy, and then they grow in size, first plowing its way through the interstellar medium of the host galaxy, and then through the intergroup medium and generally into the intergalactic medium later. And some of the largest sources we know today are over several megaparsec in size. And trying to understand the evolution of these sources and their interactions with the cosmic web are interesting aspects to explore as well. Here is an example which is called Minkowski's object. It's in a cluster Abel 194, and what you see in purple is the radio emission, and the object in the right is the one where radio emission, a shorter jet from NGC 541, which is on the lower right, it collides with a cloud of hydrogen gas, which is shown in dark blue, triggering to star formation. So here you have a live example of a radio jet interacting with the surrounding environment. So these are aspects which are important in terms of trying to understand the evolution of the environments of these sources. I mentioned a little while earlier about giant radio sources. Many years ago, in late 90s, when we were compiling a sample, that there were only about 50 giant radio sources known. A more recent compilation we have made extends it to over 350. They are defined to be over about 700 kiloparsec in size, over about 350 such sources known, and this is the largest one which we found many years ago from combining both GMRT as well as VLA and Effelsberg observations. We needed low frequencies sensitive to large scale structures to be sure that the outer lobes are connected. It extends to a size of about 4.69 megaparsec in size. So one can try and look at the dynamical evolution of these sources and estimate what its age might be, what the properties of the external environment might be, and the estimated age of this object is about 47 million years or so. This is another giant radio galaxy which was discovered using the GMRT by Pratik Devade, which is superimposed on an SDSS image. I must stress that because the outer lobes of emission are diffuse and have a steep spectrum, that low frequency telescopes such as the GMRT are ideal for discovering such objects and probing these largest scale, single scale structures that we see in the universe, single objects that we see in the universe. Now as the sources evolve and become large and giant, what happens to them? Do they just die, or does it live forever? Now here is an object where there seem to be relic lobes of emission, and this source is a very large source, and it's about 1.4 megaparsec in size, and you can see the structure. This is the GMRT image which we had made at low frequencies at 333 megahertz, I think, and you can see the lobes are very diffuse with It doesn't have the classic FR1 radio structure either. It is as though the hotspots have not been fed with energy, and if they are not fed with energy, these high energy electrons are going to keep radiating away, and they are going to age, and they are going to steepen, because there are no high electrons will continuously get depleted, high energy electrons which are radiating at high frequencies, leading to a steepening of the radio spectrum. So this is what you can see in the spectrum, and from that a spectral age has been estimated. Estimates of spectral age have a number of caveats, but it gives you a first order estimate, and this one is about 150 million years was the estimate of this object. So these are diffuse regions of plasma pervading in space, scales of 150 megaparsec or so, and sometimes actually they may reignite. And understanding these objects is important to try and understand that do all galaxies actually go through an AGN phase? Now, although we said that radio galaxies are associated with elliptical galaxies, that if you take a large sample of just elliptical galaxies and find out what fraction of them are strong radio sources, you will find that fraction is very small, less than about 10% or so. And that is also true of quasars, as we mentioned earlier, that only a small fraction are luminous in the radio, they largely are radio quiet or radio weak. Now, we're not very clear, it's not very clear whether all galaxies go through an AGN phase, or there are some special properties perhaps related to the spin or properties of the black hole which help it to trigger a radio jets and radioactivity. Now, here we see that there are two pairs of radio lobes, there are two cycles of activity. So the nucleus of the AGN has gone quiet, and then it decides to reignite. So these have been called double radio galaxies, and it may give us some interesting clues towards understanding the radio loud and the radio quiet dichotomy as well. Now, if one wants to look at the time scales of this activity, because they are very large, the large ones were identified in the early surveys that were made. One can go and estimate the spectral age, and if I look at the spectrum of the inner compact double, and I know it's a double radio source because the spectrum is steep, I can look the structure of the hotspots, and if the outer lobes were missing and not there, I would call this a double lobe radio source as well. And this one, as you can see in the spectrum of the inner double, there is no evidence of steepening at all. So high energy electrons are being supplied, and the spectral break, there is no spectral break seen, so there is a lower limit which has been put into it. If we have millimeter wave observations, then we can extend it to higher frequencies. So the spectral or the dynamical age is less than about 2 million years or so. So you can see the larger one ranges from 50 to 150 million years. So that helps us to put the time scales of recurrent or episodic activity in this AGN. What we have been trying to do recently is actually see if smaller sources also show this kind of activity, so that we can look at the range of time scales over which AGN activity can recur, and we find that it can occur on much smaller time scales as well, hundreds of thousands of years or even less. And this is an ongoing project where we have found a lot of small size radio galaxies as well. I will end today's talk or today's deliberation by showing you an example of a somewhat unique radio galaxy. This unique radio galaxy was discovered by Anand Hota, and normally, as I mentioned earlier, that radio loud galaxies are associated with elliptical galaxies. Here there is a radio loud galaxy which is associated with a spiral host in a cluster, and it appears to go 3 cycles of activity. Outer lobes are separated by about a megaparsec, and from the existing observations there is some evidence of flattening, and the suggestions that this may be due to reacceleration of particles in the outer lobes. There is a lot of evidence in normally clusters and relics and halos in cluster emission that there might be reacceleration of particles. Whether this is the case, one needs to explore further, but this is one of the very interesting objects discovered both using the GMRT and the Very Large Array. So today's lecture, I have given you a broad glimpse of the kinds of active galaxies, a brief peep at some of the emission processes and the phenomenology associated with it. In the next lecture, we will look at some of these aspects in more detail and look at the canonical model of an active galactic nucleus.